Newton's understanding of gravity was good enough to allow us to fly from the Earth to the Moon, but it's kind of got to make you laugh to think that you can go all the way to the Moon and back using something that's ultimately just an approximation. Everything in our universe seems perfect. There are laws governing the entire universe, but certain mysteries have remained unsolved despite decades of research. Why does time travel in one direction? What is the nature of reality? Why does gravity exist? Why does time slow down when we travel at the speed of light? These are questions that have fascinated us for millennia. What if I told you that gravity is a lie? It's merely a construct of the human brain. This might seem unbelievable, but that's exactly what the famous physicist Brian Cox recently claimed. Let's delve into the nature of gravity and why time slows down to find out what on earth is wrong with gravity. We need to go beyond Newton. The problem lies not so much in what he understood, but in what he failed to address altogether. There's a problem with Newton's theory of gravity, and that's that it just allows us to predict how things move under its influence. It doesn't say anything about why gravity exists, or even how it works. It just allows you to calculate things. And Newton knew this, of course. He essentially just said that it's down to God. In fact, he said that the most beautiful system of the sun, the planets, and the comets could only proceed under the dominion and counsel of an intelligent being. In other words, I'll give you the tools to calculate how the objects move around, but don't ask me how or why that is. That's down to God. In the vast universe that surrounds us, there are mysteries waiting to be uncovered. Among these mysteries are the perplexing phenomena related to time and gravity, two fundamental aspects of our existence. Imagine a world where time behaves strangely, where it can slow down or speed up, and where the force that keeps us grounded might not be what it seems. This is the realm of Albert Einstein's theories of relativity, where our understanding of time and gravity takes a strange twist. Albert Einstein, a name known to many, gave us a new perspective on the universe with his theories of relativity. His work laid the foundation for our understanding of how time behaves under different conditions, particularly when we travel at extreme speeds. It all began in the early 20th century, when Einstein proposed two groundbreaking theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, transformed our understanding of time and space. In simple terms, it tells us that the laws of physics remain the same for all non-accelerating observers, regardless of their motion. This theory introduces the concept of relativistic effects, including the famous notion that time can dilate or slow down under certain conditions. One of the most intriguing thought experiments used to explain time dilation is the light clock. Imagine being inside a spaceship moving at an incredible speed, close to the speed of light. Inside this spaceship, there's a beam of light bouncing between two mirrors perpendicular to the direction of motion. To an observer inside the spaceship, the light appears to travel in a straight line, bouncing vertically. However, to an outside observer who's not moving with the spaceship, things look different. They see the spaceship moving at high speed and observe the light beam's path. Since the spaceship is moving, the light beam has to cover more distance to hit the mirror. According to the laws of physics, the speed of light is constant for all observers, so the light beam must appear to travel a longer diagonal path. Now, here's where it gets interesting. The time it takes for the light beam to travel its path should be the same for both the observer inside the spaceship and the one outside. But since the path is longer for the outside observer, it seems like it would take more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary observer. So, in this scenario, time behaves differently depending on your motion. It's not just a concept. Experiments have confirmed these relativistic effects. For example, particles in particle accelerators like the Large Hadron Collider can reach speeds close to the speed of light. Scientists must consider the effects of time dilation to make accurate predictions and measurements. Another consequence of special relativity is length contraction. As an object moves at high speed, its length in the direction of motion appears shorter to the stationary observer. This effect is minuscule at everyday speeds, but becomes more noticeable as an object approaches the speed of light. One of the most famous equations in physics, AMK2, is a direct outcome of special relativity. This equation states that energy and mass are interchangeable. It means that mass can be converted into energy and vice versa. This principle is fundamental in understanding the behavior of particles at high speeds and the energy released in processes like nuclear reactions. Special relativity isn't just a theoretical concept. It has real-world applications. For example, GPS systems rely on the precise timing of signals from satellites. However, because these satellites are moving relative to us, this time dilation effect comes into play. If the effects of special relativity were not accounted for in the GPS calculations, our navigation systems would be significantly less accurate. The special theory of relativity forces us to reconsider our intuitive notions of time and space. It demonstrates that the universe operates in ways that defy everyday experience. Time is not an absolute concept, but is relative, influenced by motion. The constancy of the speed of
What Einstein said was this: if you don't have anything out in space, that's a flat space. If you were to take a planet, a ball, whatever it is, a rocket ship, and roll it, it would make a straight.
But the concept of curved space-time does. One of the most striking confirmations of general relativity came during the solar eclipse of 1919, when Sir Arthur Eddington led an expedition to observe the bending of starlight by the sun's gravity. According to the theory, the sun's massive presence would curve the path of light from distant stars, making them appear slightly out of position. During the eclipse, the observations matched Einstein's predictions, solidifying the theory's validity. Just as motion affects time in special relativity, gravity also has an impact on time. In regions of strong gravity, time passes more slowly than in regions of weaker gravity. This means that if you were standing near a massive object like a black hole, your clock would run slower than one located far from such a massive object. General relativity introduces the concept of black holes, which are regions of extreme gravitational curvature. The gravitational pull in a black hole is so strong that nothing, not even light, can escape its grasp. The boundary around a black hole is called the event horizon, and it marks the point of no return. Anything that crosses this boundary is inexorably drawn into the black hole. General relativity also has profound implications for the structure of the universe as a whole. Einstein initially added a cosmological constant to his equations to maintain a static universe. However, when it was discovered that the universe is expanding, he referred to this as his greatest blunder. The theory of an expanding universe, as supported by general relativity, forms the basis for the Big Bang theory, which describes the origin of the cosmos. Another significant prediction of general relativity was the existence of gravitational waves. These are ripples in the fabric of space-time itself, generated by massive accelerating objects such as merging black holes or neutron stars. In 2015, the Laser Interferometer Gravitational Wave Observatory made the first direct detection of gravitational waves, confirming yet another aspect of Einstein's theory. Over the years, numerous experiments and observations have tested general relativity, and it has consistently withstood the scrutiny. Whether it's the precise orbits of planets, the bending of starlight, or the observation of gravitational waves, the theory has repeatedly been confirmed. The statement that gravity is a lie might sound shocking, even heretical, given the well-established nature of gravity in our daily lives. However, in the world of physics, there has always been room for debate, dissent, and the exploration of alternative theories. It's not uncommon for scientists to challenge widely accepted theories. In the case of gravity, there are dissenting voices who question the traditional understanding of this fundamental force. Their arguments revolve around alternative theories, some of which seek to replace or modify our understanding of gravity. One of the most well-known alternative theories is modified Newtonian dynamics, also called MOND. MOND suggests that at low accelerations, gravity behaves differently than predicted by traditional Newtonian gravity. According to MOND, there's no need to invoke dark matter to explain the behavior of galaxies. Instead, MOND proposes that gravity becomes stronger. A key element of the debate around gravity centers on dark matter and dark energy. These are mysterious concepts that were introduced to explain certain phenomena in the universe, like the rotation of galaxies and the accelerated expansion of the cosmos. Critics of this traditional view of gravity argue that dark matter and dark energy are unnecessary, and that alternative theories can account for the observed phenomena. In conclusion, our understanding of gravity and its effects on time has evolved significantly since Newton's time. Einstein's theories of relativity have provided a new framework for understanding the fundamental forces of the universe. While these theories have been extensively tested and confirmed, there are still questions and alternative theories that challenge our current understanding. The exploration of these mysteries continues to drive scientific inquiry and push the boundaries of our knowledge of the cosmos. The question that arises is why the universe started in such a low entropy state in the first place. The explanation for this asymmetry at the beginning of the universe is still an open question in cosmology and remains a topic of active research. Quantum mechanics, the theory governing the behavior of particles at the microscopic level, plays a role in understanding the arrow of time. It introduces the concept of wave functions, which describe the probabilities of finding particles in various states. The unidirectional nature of time also raises significant philosophical questions about the nature of reality. It challenges our intuitions and our understanding of causality. We tend to perceive the past as something fixed and the future as open to possibilities. This inherent structure of time shapes our worldview and decision-making processes. The arrow of time is fundamental to our existence. It defines our experiences, the progression of our lives, and our understanding of the universe. Without the arrow of time, our reality would be vastly different. Our actions would have no consequences, and causality would be unrecognizable.